Hi everyone, this is Janine Co, aka Janine The Tutor. As you know, now is a very difficult time for each one of us, whether you're in middle school, high school, or university. Many students and families were deeply affected by the recent school closure. And as a part of OneClass, we are able to adapt quickly, and we are very fortunate that we are able to adapt quickly. That's why we are giving away 100,000 hours of free private tutoring. And on top of that, we are also hosting and running free and daily classes for math and chemistry from grades 11 to first year college and university. So if you're interested with a free private tutoring, make sure to scroll down below and book your time slot. So for today's class, we will start off with calculus and vectors. And because we finish the topics from last class, we'll just continue on with the new topic. So it's going to be very similar to what we've been learning so far. So we're looking at first and second derivative, and today we're actually doing curve sketching. So hopefully we get to that question. Okay, great. So first of all, I just wanted to make sure that you guys can see my screen and you can hear me coming through. Okay, so for the first question, right? So probably until now, right, we've been looking at first and second derivatives, and hopefully by now you are able to find the first and second derivatives by yourself, right? So for the first question, it says we need to determine the second derivative if f of x is equal to the root of 6x raised to the power of 8 minus 7, and this is the root of 7. So just to clarify, anytime you see two asterisks, right, over here, that means you're looking for the second derivative. And if it's the first derivative, therefore it's only one. Sorry, this is not an asterisk, apostrophe, right? So if you have two of them, that means this would be the second derivative. And if you just have one, that means this is the first derivative. So before you actually find the second derivative, you need to find the first derivative, right? And that's what we're going to do. So to look for the first derivative, right, we know that this has to be... Okay, so we do have a root here. So as you can see, when you write this, so this is actually equal to 6x, and this is raised to the power of 8 minus 7, and this is raised to the power of 1 over 7, because we know it's a root, right? Therefore, it needs to be raised to a fraction, and the exponent is a fraction. So in that case, we need to apply in the chain rule in this question, right? So first of all, what is the chain rule? So the chain rule just simply means that you're taking the exponent and you're bringing that down. So if you have 1 over 7, that's going to go right over here because that's your exponent. So you're bringing that down, and then you're multiplying 1 over 7 with 6x raised to the power of 8 minus 7, and then simply as the final step, you are taking your exponent and you're subtracting that from 1. So it's 1 over 7 minus 1. So that's equal to negative 6 over 7, right? So if it's negative 6 over 7, right, we're not yet done because we actually have to find the derivative of your inner term, right? Which is 6x raised to the power of 8 minus 7. So we do have to multiply that. So we multiply this too. So how do we find the derivative of this term, right? So all you're doing is you're taking 6 times 8. Remember, you're applying the power rule. So 6 times 8, that's 48. And this is going to be x raised to the power of 7. And we know that the derivative of a constant is always going to be 0. That's why this is just minus 0, right? Which we can omit at this point. Okay, great. So once we have that, right, we can actually combine our expression. So in this case, you're going to see that this can be rewritten as 48x, and this is raised to the power of 7 over our fraction, right? Because this is a negative exponent, therefore for this to become positive, you need to place that into your denominator. And this would be 7, and yeah, this is just 6x raised to the power of 8 minus 7, and this is raised to the power of 6 over 7. There we go. Okay, so that's your first derivative, right? And because we need to find the second derivative, right, it's just really easier, I find, and probably you guys too, right? I think it's easier for you to just take out the constant, right? Because remember, math is all about simplifying things, right? You don't want to overcomplicate things. So if you take out the constant, so what I mean by the constant is 48 over 7, right? If you take that out, you would have 48 over 7, and then you're just going to be left with I guess, the x expression. So you would have x raised to the power of 7, and this is over 6x raised to the, and this is still in the bracket, remember, or parenthesis. Okay, so this is 6x raised to the power of 8 minus 7, and this is raised to the power of 6 over 7, right? So I think it's just easier for you to take out your constant, right? So this, it just so happened that it's a fraction, so we're taking that out. And then we're left with this term over here, right? And I think it's just easier for you to find the second derivative if you took out the constant, or if you factored out the constant. So you're just left with this term, right, to deal with. So that's what we're going to do next, right? We're just taking this, but don't forget you still have the 48 over 7, right? I'm not saying that this is all gone, right, once you factor that out. So I'm just saying that if you're taking the second derivative, it's just easier to look at this function, right? And just remember you still have the 48 over 7 multiplying to that inner term, right? Okay, so maybe we can use purple. Okay, let's try blue. Okay, great. So we're taking the derivative, or the second derivative of this term, right? So that's what we're going to do today. And just remember, you still have the 48 over 7. So taking the second derivative, so in this case, we have the 48 over 7, right? So that's still there. Then you multiply this to the derivative of this, right? Okay, so how do we find the derivative of this, right? Because as you can see, it's in a fraction form, right? So this needs to, well, you need to apply the quotient rule, right? So the quotient rule simply implies that you're taking your numerator, right, which is x raised to the power of 7. So you take the derivative of that, you multiply that to just the denominator, which is 6x raised to the power of 8 minus 7 raised to the power of 6 over 7, and then you subtract that, right? So remember to subtract, and then you're going to take the derivative of your denominator, right? So this is 6x raised to the power of 8 minus 7 raised to the power of 6 over 7. And then, so once you've taken the derivative of that, you're going to multiply that to your numerator, which is x raised to the power of 7 divided by your denominator. So your denominator here, you're going to square that, right? So if it's 6 divided by 7 over here, you need to square that. And in that case, when you apply your exponent rules, right, when you're raising this to a power, then you're going to multiply your exponents, right? So this is 6x raised to the power of 8 minus 7. And this is 6 over 7, then you square that. Okay, so that's our second derivative, right? So now, as you can see, we still have to take the derivative of x raised to the power of 7 and the derivative of this, right? So this is, yeah, as you can see, this is a long question. So 48 over 7, so let's put that in there. So I'm kind of shifting this here so we have more space. So this is 48 over 7, and then you multiply this to, okay, so here applying the power rule, right? We know that this is 7x raised to the power of 6. You bring down the 7, and then as a result, your exponent, you subtract that with 1. That's why it's 6. And then you're multiplying this to 6x raised to the power of 8 minus 7 raised to the power of 6 over 7. And then as you can see, we're still going to apply the chain rule here because your exponent is a fraction, right? So you're going to have 6 over 7, multiply this to 6x raised to the power of 8 minus 7, and then as a result, you take 6 over 7 minus 1. So that's equal to negative 1 over 7, as you can see. So when you take this 6 over 7 minus 1, you're getting negative 1 over 7. And we're not yet done because we still have to take the derivative of your inner term, which is 6x8 minus 7. So 6 times 8 would be 48, right? So you're going to multiply this to 48, right? X raised to the power of 7. And then you're going to take the derivative of this, right? But we know that the derivative of negative 7, because it's a constant, it's 0. So we can just keep it like that. And then you just have to multiply the whole thing with x raised to the power of 7. So I'm going to do that. Okay. Great. So once we have that, we can divide this with your denominator. So your denominator, as you can see, 6 times 6 divided by 7 times 2, so that's 12 divided by 7, right? Because remember, as I mentioned, exponent laws, right? When you're raising your exponents to a power of whatever number that is, you're just simply multiplying your exponents, right? So 6 divided by 7 times 2 is actually 12 over 7. So this is 6x raised to the power of 8 minus 7, and then this would be raised to the power of 12 over 7, right? Okay, so I know the question doesn't really say you need to simplify, right? Because there are some teachers, including my teacher when I went to high school, she doesn't really require us to simplify things because it's very tedious, but let's say we want to simplify this, right? So again, it really depends on your teacher, right? I mean, the instruction doesn't really say you need to simplify, but maybe if we can simplify, I'm just going to show you how to do it, right? So, okay, let's go. So we have 48 over 7, right? And we have this term, 7x6, right? So whenever I'm saying 7x6, right, I'm saying that it's 7 times x raised to the power of 6, okay? Just so it's easier to, I guess, say and it's quicker. So yeah, just keep in mind that I'm saying that this is an exponent. Okay, so as you can see, we have a constant, right? Which is, let's highlight that just so it's easier. Okay, so we have 7. Oh my goodness. Okay, let's make this better. Okay, hopefully this is not okay, great. So yeah, as you can see, we have constants, right? We have 7, and then we have 6 divided by 7. What else? We can actually take out or factor this and this, right? So when we factor that, we can take out 1 over 7 because that's your greatest common factor, remember? So let me just write the 48 divided by 7. Okay, so that still exists. And okay, so we can take out 1 over 7, right? What else? We can actually take out x, right? Raised to the power of 6. Can you guys see that? The greatest common factor. Let's find a different, okay, this screen. So here, x raised to the power of 6, and as you can see, we have x raised to the power of 14 over here. So we can actually take out x raised to the power of 6 because that's your greatest common factor, right? So yeah, we can take that out. What else? We can actually take out 6x8 minus 7, right? And as you can see, the greatest common factor is negative 1 over 7. So we can take that out as well, right? Or factor that. Okay, hopefully you guys can see this. And this one as well. Okay, yeah, so this and this, the greatest common factor is the one that's... Okay, great. Here and here. Okay, you can take out... Okay, this is raised to the power of 6, then you have 6x8 minus 7 raised to the power of negative 1 over 7. Okay, so we've pretty much ruled out all of our greatest common factors. So now we can focus on the inner term, right? That's going to comprise your parenthesis. So when you have your parenthesis, right, you're going to see that this is 7. So inside, you can actually have, let's see, 7... Yeah, if you divided 7 with 1 over 7, you should get 49, right? And the only thing that this is going to turn out into 7 is if you multiply 1 over 7 times 49. So you're going to get 7, right? So now we took out this x raised to the power of 6, right? We also took out, so this is 1 now, right? And if we factored this and this, right? So within that, so what do you do when you're trying to factor this, right? So if you had to multiply the two terms, right, you need to add your exponents. So in order for that to even work out is if you have negative 1 over 7 outside, that means inside you would have 6x 8 minus 7, and this would just be 1, right? Because if you take negative 1 over 7 plus 1, right? Let's try that. That's equal to 6 over 7, which is exactly this. Does that make sense? Because you're trying to factor things out, so you need to think of a way to deal with your exponents, right? And if you take negative 1 over 7, if you're multiplying this term to this term, what happens to your exponents? Exponent laws, you add your exponents, right? If you're multiplying the terms. Okay, so that's done. And inside, right, as you can see, we took out 1 over 7, right? So you still have that 6 and 48, right? So 6 times 48 is actually equal to 288, right? So you still have 288. And then because, you're taking out x raised to the power of 6 and you have x raised to the power of 14 here, right? That means if you take 14 minus 6, right? This would be x raised to the power of 8, right? So when you're trying to factor things out, or you're pulling out your greatest common factor, you need to subtract your exponents, right? Why? Because you're trying to divide things, right? So say, for example, you're taking out x raised to the power of 6 here, right? If you subtracted 14 minus 6, that would give you 8. So a way to check that is after you've factored out your corresponding terms, right? Let's say you want to check whether it's right. So if you have x raised to the power of 6, when you try to multiply and distribute x raised to the power of 6 to each of your terms, if you have x raised to the power of 6 multiplying this to 288, x raised to the power of 8, you can see that x raised to the power of 6 and x raised to the power of 8, because you're multiplying the two terms, you need to add the exponents. So it's the other way around if you're multiplying versus when you're dividing. Okay. Hopefully that makes sense. Okay, yeah. So this is closing the bracket now. And then underneath that, we have your denominator, right? So this is 6x raised to the power of 8 minus 7 raised to the power of 12 over 7. Okay, great. So once we have that, right, as you can see, maybe we can combine this. Because it's a negative exponent, we can actually move that to our denominator so it becomes a positive exponent, right? And obviously, we're running out of space again, right? Okay, let's just continue on. And then for number 2, we'll just move this question. Okay. Let me just copy the second question, and then... No, we need the space for graphing. So, okay, let's just turn it into a new page. Yeah, we'll continue on number 1. I just wanted to create a new one. Okay, yeah, let's deal with question 2 later on, but I'm going to omit question 2 because we're going to solve question 2 into a different document. And yes, and whatever is written down, right, it's recorded, so you don't have to like panic in terms of trying to write this down. Okay, so let's ignore question 2. Let's just continue on from question 1. Okay, so as I mentioned, I'm going to combine this term. I don't think we've used this color yet, so I'm going to combine this term and this term, right? Because I can see that they're exactly the same. So okay, and I'm also starting to multiply 48 over 7 times 1 over 7, so I would get 48, right? And this is 7 times 7, which is 49, right? So this is going to be x raised to the power of 6 over here. So I'm just simply copying whatever I have in my numerator. And this is all going to be over 49, right? And my denominator now, because I'm adding this 1 over 7, right? So essentially when you move this down, you're going to have 6x8 minus 7 raised to the power of 1 over 7. So all you have to do is add your exponents, right? So that's why this is now 6x8 minus 7, and this is raised to 13 over 7, right? Because when this is multiplied to this term, right, and you're trying to negate the negative exponent, that would be 1 over 7, so you add the exponents because you're multiplying the terms now as opposed to dividing the terms, as you can see here. Okay, this is 48x6, and what else? We're going to deal with this term, right? So if you expanded this term, right, 49, and you have this term, right, you're applying the distributive property. So you would have 49 times 6, x8. So 49 times 6, that's equal to 294. And this is x raised to the power of 8, and you have 49 times 7, that should be 343, I believe. Yeah, 343. So this is negative 343. So I'm multiplying this and this. I get 294x8. I'm taking 49 times negative 7, so I'm getting negative 343. So I'm trying to expand my inner term. And then I have negative 288x raised to the power of 8, right? Great. So once I have that, all I have to do is simplify my numerator. So 48x6. Because these two are like terms, I'm going to combine them, right? Okay, hopefully. I meant to highlight that. Give me 1 second. Okay, hopefully you guys can see this. This and this term, right? I'm trying to combine them together. So I'm getting... Yeah, so 294 minus 288. That's equal to 6. So this is 6x raised to the power of 8. And this is minus 343. Yeah, I can actually change this bracket into a parenthesis as opposed to a bracket. There. Okay, great. We have that, and that's over 49 times 6x raised to the power of 8 minus 7 raised to the power of 13 over 7. Okay, so as you can see, we can't really simplify this further. Therefore, the final answer is this. So this is your second derivative. Okay, great. So once we've solved for that, let's move on to question 2. Okay, here it says we need to determine the absolute extreme values of f of x, which is equal to 9 square root of x minus 7x on the interval 6 comma 9, right? So first of all, whenever you're trying to figure out what the extreme values are, right, you need to remember that you're looking at your local extremas and also your global extremas, right? So when you say local, right, it's only occurring at a specific neighborhood, right? So maybe I can quickly draw that. Okay, so let's say you have a graph, right, and you have a function. Okay. Okay, so as you can see, say for example, you are at a specific interval. Okay, let's say this is 6 and 9 as an example, right? So within a specific neighborhood, right, you have your local extrema, so you have your local min, which is local minimum, and you have your local max, right, which is local maximum. So this in a specific neighborhood, right, because we're saying that in this case, right, you have your, so this is local max, right, because it's only at a specific neighborhood, right? So if you're looking within the entire domain, when you're saying it's a global max, therefore from this interval to this interval, the highest that you can go, this is your global max, right? But within this, right, because it's concaving down, right, so this is your local min, right, because it's only at a specific neighborhood, right? But if you look at, yeah, this is local min, L dot min. So if you're looking at over your entire domain, right, from 6 to 9, for example, if you're looking for your global min, that means you're looking at, I guess, the lowest peak. So in that case, the lowest peak would be this. So this is your global min. Does that make sense? So your local min or your local max is just a way to determine within that specific neighborhood, right, if it's a max or a min. However, if you're looking at the global max or min, that would depend on your entire domain, which means you're looking at a specific x until, I guess, your last interval. Okay, so this is a local max, this is a local max, this is a local min, and this is a local min, right? Yeah, this is supposed to be a turning point, not a corner. Okay, great. Yeah, so you pretty much got a gist of, what's global min and global max, and as well as local min and local max, right? So now we're looking at this function, and it's on the interval 6 comma 9, right? So the first thing that you actually do is you look at the first derivative, right? Because you're looking at your extremas, right? You're looking at your critical values. So you have the first derivative of x, right? So how do you find the first derivative of this? So because you know that this is 9 and you have x raised to the power of 1/2 minus 7x, we can actually say that you can bring down the 1/2, right, applying power rule. So you would have 9 over 2, right? And why is it 9 over 2? Because you're bringing down the exponent, you're multiplying that to your coefficient. So 9 times 1/2 will give you 9 over 2. And this would be multiplied to x. And as a result, you would take your exponent minus 1. So that would give you negative 1/2. Great. Now, if you look at negative 7x, therefore the derivative of this, right, this would just be negative 7. Okay, so once you know that this is your first derivative, you're going to equate that to 0 because you're looking at your extremas, right? That's what we do. So you're looking for the critical values. Okay, so guess what? Because we have this negative 7, that means you need to move this to the opposite side of the equation. So you would get 9 over 2, right? And make sure that you turn this back into square root of x, right? And that belongs to the denominator because you have a negative exponent, and that's equal to 7, right? As a result, you would have to multiply 2 square root of x with 7. So therefore, you're going to have this 9 is equal to 7 times 2 square root of x is going to be 14 square root of x, right? And the reason why I'm doing that is because I want to isolate x, right? I mean, math is all about finding x, right? Or even algebra. So that's 14 square root of x, right? So that's divided by 14. And why is it divided by 14 for both sides? Well, we want to isolate x, right? So yes. So we have 9 over 14 in this case. So this is square root of x, and how do we get rid of the square root? Well, we have to square both sides, right? Squaring both sides would give you 81 over 16, and this is equal to x, right? Because 1/2 times 2, right? That's equal to x. Okay, so we have this, right? And sorry, this is 14 squared. It's not 16. For some reason, I read that as 4. Okay, 14 squared is 196. There we go. Okay, so if you try to punch this into your calculator, 81, okay, do this like right now. 81 divided by 196. So this is equal to 0.4, right? About 0.4, right? And if you look at our interval, right, it's actually 6 comma 9, so it's not within that interval, so you can't really use that. So this is not in the interval. Therefore, you can't really use that, right? So what we're going to do right now is we're taking 6 and 9 and we're plugging that into our function, which is f of x, this f of x over here. Okay, so f of 6, right? So we said it was 9 square root of 6 because it's square root of x minus 7x. So minus 7 times 6, right? So we're looking for this value, right, when x is equal to 6, and we're looking at when x is equal to 9, right? So 9 square root of 9 minus 7 times 9, right? And the only reason why we're doing this is because your extrema does not fall between 6 comma 9, right? That's why we're doing this. Okay, so get your calculator, type this in. So you have 9 square root of 6 minus 7 times 6. So this is equal to negative 42, right? Plus 9 square root of 6, right? Which is about negative 19.95, right? And then on the other hand, if you type in 9 as your x, So plug in 9 over here and here. So you would have 9 squared of 9 minus 7 times 9. That should give you negative 36, right? So comparing the two values, right? So we know that if you're looking at the minimum versus the maximum, you're actually comparing your y values, right? Which is respectively negative 19.95 for 6 and negative 36 if it's 9, right? So as you can see right off the bat, we know that this is the lowest value, therefore this will be your absolute min, right? So absolute min, and your absolute max is this. Okay, great. So yeah, the question going back to this, determine the absolute extreme values of f of x on the interval 6 comma 9. So you can just say that your absolute min is at 9 comma negative 36. So 9 comma negative 36, right? X is 9 and negative 36. And by the way, 9 is included, so that's why you need to make sure that this is included. And then you have negative 36 over there. Then your absolute max is going to be it's 6 comma negative 42 plus 9 square root of 6. Great. Okay, so yeah, but typically when they're asking for absolute max or min, you can just keep it as this and this, right? You don't really need to write it as an interval because you don't know what exactly is happening on negative 36 and this. So I don't think this is even necessary, so let's not just bring that up. But I just wanted to show you it's an x and y coordinate, right? I mean, that's how min and max work. Yeah, if they're just asking absolute min, you can just say it's negative 36, and your absolute max would be negative 42 plus 9 squared root of 6. That's it. Okay, let's not overcomplicate things. Okay, great. So we're going to go to optimization. So optimization basically just means that you're trying to look for the area, the cost that's going to maximize the profit or the area in that case. Yeah, so that's optimization for this course, right? I guess for the scope of this course. So let's look at this garden. So we have a rectangular garden. It's to be planted against the side of a barn. The gardener has 433 meters of fencing and will construct a three-sided fence. The side of the barn will be the fourth side. Determine the dimensions of the fence that will give the garden the maximum area. Okay, so apparently your garden, you only have a three-sided fence, which is looking like this, right? And it's supposed to be a rectangular garden, so that's why I know it has to be in this shape. Great, so the gardener has 433 meters of fencing, so that means this whole thing, it's actually 433 meters, right? And we know that this is going to be your length and this is your width, right? The side of the barn will be the fourth side. So this is where the barn is. Determine the dimensions of the fence that will give the garden the maximum area. And if you recall, whenever we're trying to find the area of a rectangle, it's just length times the width, right? So because again, whenever we're optimizing things, right, in calculus, you need to make sure that everything is using the same variable. So you can't just have length and width and trying to optimize things. So you want to express them based on one variable. And for today, we're using x. So let's say I let w, which is equal to x, right? I know that w is equal to x, but how do I find my length, right? How do I express length in terms of x? Right? So for length, we know that the whole thing is actually 433 meters, right? If you think about it, this until this is 433. So we're taking the whole thing, 433, and then we're going to subtract that with twice your width, right? Because you have this part over here and you have this part, which is your width, right? Does that make sense? That's why it's minus 2x, because we said that w, or your width, is actually x. So that's why it's minus 2x. Because we wanted to take just this part, right? So how do you find length? You're taking 433, which is the entire, I guess, dimension of your garden, right? The fencing rather. So it's 433 minus twice of your width, right? Because if you cut this into segments, basically you have twice of your width and then you have your length. Make sense? So that's the first thing that you need to remember when you're trying to optimize things. You need to have the same variable. Okay, great. So now that we know what the width and the length is, you can actually say that this is a of x, right? So you're finding the area with respect to x. So I said it's going to be length times width, so it's 433 minus 2x, and you're multiplying that to x. So this is 433x minus 2x squared. Okay, so we know what the area is with respect to x, right? So it says determine the dimensions of the fence that will give the garden the maximum area. Okay, so here's the thing where you start optimizing. So in that case, for you to find the maximum area, you need to look at the first derivative of your area. So a, the first derivative of x, right, is equal to, so you're going to take this and you're deriving that, right? So it's 433 minus 4x, and this is just x, right? Because we know that this 2, right, you're applying the power rule. So you bring down 2, you multiply that to negative 2 to give you negative 4x. And as a result, your exponent, you subtract that with 1. That's why it's just x. Okay, great. So we now have that, right? And how do we find the maximum area? Well, you need to look at your critical points, right? So your critical points, it's based on when a of x, when you're looking at the first derivative, and that's equal to 0. Right, so you have negative 4x, which is equal to 433, dividing both sides with negative 4 to isolate x. So x is equal to, let's see, 433 divided by negative 4. Actually, this should be negative 433 because you're moving this to the opposite side of the equation. And just as a reminder, right, let's say you want to know or you want to check whether your answer is right, you actually have to remember that dimensions always needs to be a positive number. So if you're wondering, okay, so I'm dividing a positive 433 with a negative 4, right, it doesn't make sense for dimensions to be negative, so you need to go back and check your work. Yeah. So you have 433, moving that to the opposite side, you get negative 433. And as a result, you divide this with a negative number, so that becomes positive, right? So it's negative 433 divided by negative 4. So this is actually equal to 108.25. So because we said that x is your width, right? Can you guys see this? So you can actually say that this is your width, and going back to the question, we're using meters. Therefore, your width is 108.25 meters. That's your width. And then how do you find your length? Well, obviously you have to take length is equal to 433 minus 2 times x, which is 108.25, right? So that's your length. So 433 minus 2 times 108.25, that's equal to 216.5. So this is meters and this is your length, right? Okay, so now that we have our length and width, okay, now the question is determine the dimensions. Yeah, that's pretty much it. So that's your width and that's your length. So those two will give you the maximum area, right? And if you want to know what the maximum area is, then all you have to do is you multiply this and this, right? Okay, great. I don't think that was too bad, right? Again, whenever you're optimizing in calculus, you're just looking for the first derivative. And when that's equal to 0, then you solve for the dimensions and whatever is being asked. Okay, great. So we finished that. Okay, so now let's look at a different way of, I guess, optimizing, right? So now this is all about costs and, yeah, it's cost and basically production. Okay, so we have the cost in dollars to produce X amount of t-shirts for a certain company, which is modeled by the function C of X, which is equal to 4.4x plus 0.007x squared, where X is greater than or equal to 600. How much production is needed to have a marginal cost of $10.11 per t-shirt? Okay, so first of all, The reason why they're saying it's marginal cost is because it's the cost of producing an extra quantity or one quantity in general. So if you have this function, c of x, right? And guess what? Because we're optimizing, right? It says how much production is needed to have a marginal cost of this. So you're going to find the first derivative of c of x. That's basically the first step. So let's go and do that. So the first derivative of c of x, this is going to be 4.4, right? The first derivative of this is 4.4 because all you have to do is take 1 times 4.4 to give you 4.4. And as a result, the exponent of x is 1 minus 1, therefore it becomes 0. So you don't really have an x here, it's just simply 1. And then this is added to 0.007 times 2, right? So this is actually equal to 0.014. So multiplying this coefficient, 0.007 times 2 would give you 0.014. So this is times x. And yeah, that's it. That's the first derivative. Okay, great. So because you wanted to have the marginal cost of $10.11, that means you're not equating this to 0. Does that make sense? So that's the only difference, because you wanted to have a cost of exactly 10.11, right? That's why I'm going to equate this as 10.11, right? So as you can see, we can move 4.4 to the opposite side of the equation, right? So you have 0.014x, which is equal to 10.11 minus 4.4. That's equal to 5.71, right? Dividing both sides with 0.014. So x is equal to, so 5.71 divided by 0.014, this is equal to 407.86, right? 407 point, yeah, this is about 407.86, right? And because we're saying that we're producing X amount of t-shirts based from the question, we're saying that X is the amount of t-shirts that that the company is producing, right? So I mean, we can't have 407.86 t-shirts. Like, you cannot have 0.86 t-shirts, right? Therefore, we're going to say that we're rounding this up into 408 t-shirts, right? Okay, now that you're going to think about this, right? It says your x needs to be greater than or equal to 600. That means the question is telling you that you want to have a marginal cost of $10.11, right? And on top of that, you need to produce 600 or more t-shirts. Does that make sense? So you can't really have that, because as you can see, if you want the marginal cost to be $10.11, you can only produce 408 t-shirts. So this is actually not possible, right? So not possible. Yeah, does that make sense? So that's why how much production is needed to have a marginal cost of 10, 11 t-shirts, 10 $11, and that's per t-shirt. Well, yeah, you can only produce 408 t-shirts if you want to have a marginal cost of $10.11. So that means producing 600 or more t-shirts at a marginal cost of $10.11 is not possible. Okay, hopefully I've emphasized that enough. I don't think optimization is that hard, as long as you are able to read through the question and kind of understand it in a way that you know what they're asking for. I think that's the most important part, I think. And I think a lot of students, based from, from my experience, they just have trouble reading the question and seeing what the question is asking for, but they know their math. Does that make sense? So I think you just need to practice and just read so many questions that at this point on, you are able to understand what the question is looking for. Yeah, I think that's just the trouble, or I guess the issue with word problems in general. I mean, even in the sciences, right? So yeah, math is all about practice. Okay, great. So you have number 5, right? Okay, so here's an interesting question. So now we're looking at position, we're looking at velocity, and we don't really have let's see. We have average velocity, we have instantaneous velocity, and we have position. Yeah. So I just wanted to tell you guys right now, basically in calculus, I know there is an overlap between physics and calculus and like the graphs, position, time graphs, and all that. But I guess for this part, we're just talking about position being the function, which is s of t, as you can see over here. And then we're looking at the first derivative of s of t. So when you say s of t over here, this is basically your velocity of t, right? Velocity over your time, right? Function. And then if you're taking the second derivative of your function, that's basically acceleration, right? I think that's where calculus and kind of physics overlaps. But yeah. So for this question, we're looking at the average velocity between t is equal to 8 seconds and t is equal to 21 seconds. And you have a particle which travels along a straight path in a way that its position in meters can be expressed with the function s of t, which is equal to 10t raised to the power 5 minus 8t raised to the power 4. Okay, because they're looking for average velocity. Okay, so here's the thing. You need to familiarize yourself with average rate of change and also, well, in this case, average velocity and instantaneous rate of change or instantaneous velocity. So when they're looking at average velocity, it means it's average rate of change, and therefore you need to remember that you're looking at your slopes of secant, right? And if you're looking for instantaneous rate of change or velocity, you're looking at the slope of your tangent. So yeah, those are just two things that I think you should know by now. Okay, you have s of t, which is equal to 10t5 minus 8t4, right? We need to determine the average velocity. Okay, so if you remember, how do you find the slope of your secant? Well, all you have to do is plug in s of, so this is t1 first of all, and this is t2, right? And how do I know this is t1 and t2, or t initial and t final? Well, your starting point is 8 seconds, and then you're moving towards 21 seconds, right? That just makes t final or t2 21 seconds, right? So it's always going to be s of, or your, I guess you can just say this is delta y over delta x, right? So your delta y would be your function, right? Remember when we say if it's a function, it would be y. So in this case, you're taking the second one. So it's a change. Remember, it's the second one minus the first one, or final minus initial. So you're taking s of 8. And in your denominator, because you know that t is your x, therefore it's going to be 21 minus 8. Because delta, right, as a Greek letter, it just means it's change, which is 2 minus 1. Okay, great. Or not 2 minus 1, but final minus initial. Okay, great. So we know that this is s of 21, right? So all you have to do is plug in 21 over here and see what it gives you. So maybe we can do that quickly. So s of 21, I'm just taking 10 times 21 raised to the power of 5. And then I'm subtracting this with 8 times 21 raised to the power of 4, right? Okay, great. So this is a huge number. So this is 392,85162, right? And then on the other hand, if you plug in 8, right, over here, this would be 10 times 8 raised to the power of 5 minus 8 times 8 raised to the power of 4. So yeah, you're going to get 294,912, right? So yeah, all you have to do is take this number. So this is 392,85162, and this is minus, maybe we can bring this down. Yeah, I'm just going to write this again because I want to make sure it's aligned. So 392,85162 minus this number, which is 294,912. And this is going to be over 21 minus 8. And yeah, all you have to do is plug this into your calculator. Okay, so 392,85162 minus 294,912 divided by 21 minus 8. So yeah, this is 2,99250. So yeah, this is 2,999,250. So that's in, because it's velocity, it's meters per second. So that's your final answer. 2,999,250 meters per second because it's velocity, right? Velocity is basically distance over time. So we're taking meters per second. Okay, great. So determine the instantaneous velocity when t is equal to 8 seconds. So for this question, that means when you're looking at instantaneous velocity, you need to remember that you're taking the first derivative of your position function, right? So you're taking the first derivative of s of t. That's what instantaneous velocity means. Great. So this is v of t, right? So 50 t4. So yeah, I'm just taking my 5, multiplying that to 10. So it's actually 50 t4. 50 t4, and what else? This is minus 8 times 4 is 32, right? T cubed. Great. So this is my v of t, and instantaneous velocity, because it's at t is equal to 8, right? Therefore, you're going to find v of 8. So 50 times 8 raised to the power of 4 minus 32 times 8 cubed. So plug that into your calculator. So this is 50 times 8 raised to the power of 4 minus 32 times 8 cubed. Yeah, this is actually 188,416. Okay, let me move this a little bit. There we go. Okay, yeah, so this is meters per second. Again, because it's velocity, right? It's meters per second. I mean, that's the unit for velocity if it's expressed in meters for your position. So yeah, that's that. Okay, so I guess we can squeeze in another question. I think this is going to take a while, but hopefully you guys are still there. Okay, so let's get into it. So we have to find the exact maximum volume. Okay, here's the thing. Optimization, it screams maximum of whatever units they're asking for. So here, I guess we've talked about maximum area, and then the other one was you need to produce this amount, right? So that's still optimization. And then here it says find the exact maximum volume of a cylinder, of a right cylinder, that has a total surface area of 491 pi, and this should be centimeter squared. Yeah, for some reason I don't know why I guess why the subscript becomes smaller for some reason. I guess superscript, yeah. This is supposed to be centimeter squared, by the way. So the 2 should be a superscript. Yeah, for some reason this app just turns it into a subscript. So just bear in mind that this is centimeter squared. Okay, so we need to find the exact maximum volume. Okay, so they're telling us that the total surface area is 491 pi centimeter squared. Okay, so if you recall, right, the surface area of a cylinder, so let me call that as SA, right, surface area. The surface area of a cylinder is actually equal to 2 pi RH, right, plus 2 pi r squared, right? Because you're also taking, because it's a cylinder, right? The base of a cylinder is actually a circle, therefore you're taking the area of a circle as well, right? Which is 2 pi r squared. And you have 2 circles, right? Because it's a cylinder, right? The top and the bottom, basically the bases, there's 2 of them. That's why it's times 2. Okay, great. So you know that. And this needs to be equal to 491 pi, right? Because the total surface area is 491 pi. Now, for the volume of a cylinder, right, this is something that you need to know as well, right? Because I think for calculus, a lot of teachers, they don't give you a formula sheet, so you need to know this. So if you're looking for the volume of a cylinder, it's actually pi r squared h, right? So we know that this is the volume of a cylinder, and you know that this is the surface area. Okay, so we're good to go. But the problem here is you have 2 variables, right? I mean, excluding pi, but if you look at r, right, that's one variable, and you look at h, that's another variable. So it's not the same variable, right? So that means you need to find a way for r and h to be expressed as the same variable, right? So what I did was I took the surface area, I isolated h, right, and expressed h in terms of r, right? So here's what I did. So I took this thing. So I said, okay, you have 2 pi rh. This is plus 2 pi r squared, and this is equal to 491 pi, right? So as you can see, there is an h here. So I isolated h, right? I mean, that's the easiest because you have an r here and you also have an r here. So you don't really want that. Okay, so all you do is you take 2 pi rh, right? Isolate that in one side. And then you take 491 pi, you move this 2 pi r squared to the opposite side. So this is minus 2 pi r squared, right? And what else? You can actually divide this with 2 pi r from what I'm seeing here. 2 pi r. There we go, 2 pi r. Can you guys see that? So I'm canceling 2 pi r. And then I'm left with h. And as you can see, you have a pi here, so you can actually factor that out. So you would have pi. And the only reason why I'm factoring pi out is because I want to cancel the pi in my denominator. So I have pi and you have 491, and this is minus 2r squared. And this is 2 pi r, right? Can you guys see that? I can cancel out my pi once I factor that. Okay, great. So I've expressed h in terms of r. I mean, that's the goal, right? So we have h, and this is 491 minus 2r squared divided by 2r. Okay, so once I found, h expressed in terms of r, I go back to my volume, right? So I go back to my volume, and you know how there is an h here? I'm going to substitute, right, this term in replacement of h. Does that make sense? Because I want to express everything in terms of r. Because remember, this is optimization. You're supposed to express your variable just as a single variable. You can't have multiple variables. There's no way you can solve h and r simultaneously. So yeah, I'm just taking my volume, right? So I know that my volume is pi r squared h, and I'm taking this h, now I'm plugging in this term as my h. So I have 491 minus 2r squared over 2r, right? Okay, great. So I now have that. Okay, so let's see if we can simplify this, right? So if you wanted to simplify this, okay, let's see. We have 2r. Yeah, so what you can do here, you can actually first cancel out your r, right? Because this is multiplication. So you have an r here and you have an r here. So you're left with pi, and this is r multiplied to 491 minus 2r. Let's see. Yeah, minus 2r squared over 2, right? Okay, great. So I've gotten rid of my r in my denominator. Now, maybe if we can split this into two fractions, right? So let's split that up. So we have pi r, then you multiply this to 491 divided by 2, and this is going to be minus. So because you have 2r squared here, so you can actually cancel out the 2, right? So essentially this thing would be negative 2r squared over 2, right? You can cancel out the 2. Can you guys see that? So that's why it's now going to be negative r squared. Okay, great. So we've separated, I guess, the terms into two fractions. So we have this, right? So now what you can do is you can distribute pi r. So this is 491 pi r divided by 2. And this is minus, let's see, pi r cubed, right? Yeah, pi r cubed, because when you're multiplying r and r squared, that gives you pi r cubed. Okay, great. So now that we have that, that means your volume expressed in, okay. So yeah, going back to what I said, your volume expressed in r is this, right? So we now know that v of r, right? I should have just written this as v of r, but as a function of r, this is your volume, right? So great, we actually satisfied one of the conditions. We need to express our function base in just one variable, which is now r, right? And that's what we wanted. Okay, but we're not yet done because we need to find the maximum volume. And because we need to find the maximum volume, we need to find the first derivative of r. Okay, so because it's 3 p.m. right now and the class is supposed to end at 3, I'm just thinking we can just continue on finding the first derivative of the volume. So let me just note that so we know where to go back to for next class. Okay, let me just write that down. So this is question 6. So we said V of r is equal to 491 pi r squared. And this is divided by 2, I believe. Let's see. Sorry, pi r divided by 2. And this is minus pi r cubed. Okay, great. So yeah, let's just continue on. So for next class, we will be covering and we're looking for the first derivative of your volume, right? Because we wanted to find the exact maximum volume, right? And when we find the first derivative, we need to equate that to 0. That's what we need to look for because we're optimizing. Okay, great. Yeah, thank you so much, guys, for tuning in. I really appreciate that you attended my class and just listened to an hour of me talking about calculus, because I guess for all of the math courses, fun fact, calculus is my favorite so far because I had the best teacher, and hopefully you like calculus as much as I do. Yeah, thank you so much, guys, for tuning in. And for my next class, it will be on Friday, so I'll see you on my next class. Bye, guys.